So we're gonna start recording. All right. So, all right, we've got it's April 13th. We have 6 more days of class. Still have a lot to do, but we're actually making pretty good progress. So there's that. I have uploaded a new homework. So keep checking, the files page on Canvas because I've got all sorts of solutions and new homework and all sorts of stuff posted. So that can be a pretty good resource. And so today you can see we're going to do something called flux integrals over surfaces. So you might be like, all right, we've done so many different kinds of integrals, it's hard to keep track of everything. So let me just kind of tell you in order, remind you of all the different kinds of integrals that we've done so far. So a reminder of all different types of integrals. You've done. Okay, so I should open the chat actually so I can see the chat. The first thing that we did, the first one was we did double integrals over solid regions in the plane of some function dA. Now we could have done that in Cartesian or polar. Okay, then the next thing that we did was triple integrals of some function over solid 3D regions. And we had a whole plethora of options to do an integral that way. We could have used Cartesian, cylindrical, or we did spherical. Okay, so that was midterm 1, midterm 2. No, and then actually also on midterm 1 we did scalar line integrals over a curve. Then what else did we do? We did scalar line integrals over surfaces. Okay. In fact, I'm going to need to shrink all of this because I want to make room for the 2 more things. Okay. And then, so I guess this is the one I want to talk about for a sec. This was like, we had some surface, some S in 3D space, parameterize, and we, if there was some mass density, if it was made out of tin foil, then if we integrated the tin foil, we would get the mass. Okay, so that was 4. 5 is when we started doing integrals with vectors in it. So that's when we did some things like a vector field dotted with a unit tangent vector along a curve, ds. So this is a circulation integral. So all sorts of things we've done so far. And today, what we're going to be doing is the 6th kind of integral, which is the following. It's a double integral. It's going to be over a surface. And what we're going to be doing is we're taking a vector field that's present everywhere, and we're going to dot it with a normal vector, normal to the surface. Now that's a function over my surface in 3D space. So I'm going to integrate it with respect to area. And this is called a flux integral over a surface. And this is going to be, if any of you take electromagnetics, E&M, or are into physics, this is you'll be doing this a lot with electromagnetic fields, where V is your electromagnetic field. All right, so that was just, so let me kind of draw what this thing looks like. So we are doing, okay, so flux integrals over surfaces. Okay, this is page 2. So what do we need? What are the ingredients that we need? So 1, we need a surface in 3D called S, which is oriented. Oriented means there are 2 sides of the surface. There's a positive side, or a side that you call positive, and an opposite side, which you might call negative. So it's something like this. So that's a pretty good example of a oriented surface. You've seen me draw this plenty of times, just kind of like a wavy sheet, you know, kind of blowing in the wind like a flag. So just, I know you might be like, what the heck do I mean by oriented? Just remember that the Mobius band is an example of something that isn't oriented. So non-example would be the Mobius band, which kind of does this thing with a twist right here. Because if you know, hopefully you've all seen this before, but if you try to stay on one side of the piece of paper and you follow it all the way around, you'll get onto the other side. So this really is not an oriented surface. Oriented surface. It's non-orientable, but you don't really need to worry about that too much. Okay, so this is good, this is bad. The second thing that you'll want is along your surface, we have a unit normal vector field. Okay, so it's oriented positively, meaning it's pointing through the positive side of the surface. Okay, so I'll draw the picture. So if this is my nice flag-like piece of cloth in the wind, then a unit normal vector field, so okay, this is S, a unit normal vector field might be something that points out like this at every spot. Okay, so it's orthogonal or perpendicular to the surface at every single point, and it is of unit length everywhere, so that would be my N. And finally, the third ingredient you need is a vector field. Okay, so you need, we have some V of X, Y, Z. So we're in 3 space, so we need 3 inputs. So that's what we're doing. So it's like, maybe I'll draw some green vectors out here that kind of come through the surface a little bit. So there's a red vector field and then there's a green vector field. Okay. And the green vectors are everywhere, all over, but the red vectors are restricted to the surface. So the reds are stuck on the surface, but the greens can kind of be all over the ambient space. And so the integral we're going to be computing is we're going to go over the surface. We're going to rack up a whole bunch of values over the surface. And at every point we're going to get a number. And that number is the dot product. It's taking the dot product of V with N. So you can kind of see that this number is going to be bigger at a point if the green and red are more parallel with each other. And it's going to be really negative if the green is going opposite the red at every point. And we'll get 0 if the green isn't really going through the surface at all. So really, this is measuring an accumulation. This measures an accumulation of how much V is flowing through to the positive, I guess, no, it's flowing through surface F. Through surface S, sorry, okay. When this integral is super positive, that means the green is really flowing a lot through the red, through the surface, and if it's 0, and maybe it's not even flowing through it at all. You can think about this as another way of like, your S is a fishing net, and the green arrows are showing you the velocity of the sea's motion, like the water moving in the ocean. And the overall integral is going to tell you, you know, how much the water is really flowing against your net. And if it's positive, then you might think, oh, I have a chance of catching a lot of fish, because you think that the fish probably are going to some degree move along with the direction of the surface. Okay, so that's the theory of what we're setting up. We haven't really done any math yet, but okay. So on this next page, I'll tell you exactly how we compute this thing when we have a parameterization. Because right now, this is just a theoretical symbol right now. How do we actually do it? Well, let's see. So let's go to page 3. All right, so how do we compute this flux integral? Okay, well, remember when we did scalar surface integrals? Remember, in some sense, this is a scalar surface integral, because this is, after you take a dot product of a function, this is just a collection of numbers distributed over a surface, and we have had practice in computing an integral of the sort. So when we did that, what we needed to have was a parameterization of the surface. So the very first thing you'll always want is start with a parameterization of the surface of S. So that's an R of U comma V, which has 3 components, X, Y, Z, and each of those are functions of U and V. Okay. And then, your U will probably go from A to B, and your V will go from C to D. Typically one of these are 0 to 2 pi, as you've probably had enough practice with by now. Okay. The next thing you'll have to do, remember to compute the dA, you have to compute the partials and the absolute value. So you'll want to compute that dA is the magnitude of the cross product of these vector fields. This is du dv. Okay, that's going to be, that is this piece right there. So you can't really leave that out, at least for now. We'll see a trick where you can actually kind of eliminate having to do this step, but for now, this is what you'll, in theory, what you need to do. So the next thing you'll want is, you do have this vector field, v of x, y, z, but instead, remember, we're going to be doing this integral. This will turn out to be an integral in u and v coordinates. So you want to convert to parameter coordinates. This is just replacing anytime you see an x with your x of uv and your y of uv and your z of uv. And so what you'll now have is a vector field that only depends on u and v. Okay, and that is almost everything, because look, if you look at the integral up top, okay, the s is defined by the parameterization. The dA you'll compute using this thing. The v is taken care of by subbing in the u and v. So the last thing you have to deal with is the normal. So let's discuss the normal vector. So to get a formula for the unit normal vector field, well, remember, I think we've done enough pictures where, remember that partial u and partial v are tangent to the surface S. So their cross product gives you a vector that is orthogonal to the surface. So thus, partial u cross partial v is normal to the surface, is orthogonal to the surface, but it might not have unit length. So thus, if you divide by the value, the absolute value of the magnitude of the vector, so you can have that n is partial u cross partial v over its length, partial u cross partial v. So now you're guaranteed to get something that is orthogonal to the surface, and this piece down here guarantees unit length. And I'll say one thing here, a little caveat. Lots of times it matters if you do partial u or partial v, whichever one you do first. So I'm going to say plus or minus. You'll have to check if the thing you've computed is the one that agrees with the normal vector in question. So if that doesn't make sense now, it'll definitely make sense. We'll just do a whole bunch of examples for the rest of the class, and I'm going to resize this because so the last thing we'll do is we'll assemble the integral. So finally, So to put it all together, here's the formula for the actual flux integral in question. It's a double integral. Well, S v dot n dA is going to look like the following. Okay, so the integral becomes a to b, c to d. So we're going to have a du dv. All right. Now let's write. Okay, I've got it in purple up top, so I'll keep that purple. All right. So we've got v of u comma v dotted with. All right. I'll call the green up there is n. So dotted with my n. So I'm going to write plus or minus partial u cross partial v. This is this chunk right here over the magnitude of partial u cross partial v. Okay, that's a dot product. That's a purple dot product with this vector right here. And then finally, I want that dA. So, okay, actually, I'll just write everything. This was n. This is v. And now for my dA, you'll see dA is this thing right here. So I've got to multiply by that magnitude of partial u cross partial v, so that this thing right here becomes dA. And you'll see something nice happens that kind of also happened when we did circulation integrals, that you see that something cancels, that absolute value actually cancels off. Not absolute value. I keep saying absolute value when I mean magnitude. So to actually simplify matters, this whole thing becomes C to D, A to B, V of UV, dotted with partial U cross partial V, because a plus or minus, in case we get the sign wrong, du dv. And this is how you actually compute it in question after you have a parameterization. Okay. So I'll pause, I'll see if there are any questions, and then I'll kind of jump into example. It probably always at this point when I introduce how to do an integral, it's like okay, this seems like crazy. I don't know if this is actually is any more simple to you all than this symbol right here, but this really is like the recipe for how you set it up. Now Jamie says in step 2, it looks like partial u cross partial u. Partial. It's always partial u cross partial v. It's always partial u cross partial v. Thank you for that. Yep. Partial u cross partial v, or it might be partial v cross partial u, but partial u cross partial u is just going to give you dead zero because you take a cross product. Yeah, okay. So let me flip over to this next page, and we're going to do an actual example. And I'll write up that thing at the, okay, so the recipe is, that's not how you spell it. Recipe, there's no E. Ugh, okay. The flux integral v dot n dA is this thing, C, D, I'm just copying from the last page, A, B, V of U, V, dotted with partial U cross partial V, that's a vector, it gets dotted, and then it's du, dv. Okay, so that's what we got on the previous page. Let's do an example. All right, so S is the widely opening cone given with the following parameterization. So R of UV is 2V cosine U, 2V sine U, and V. Where U, you can already see it's playing that theta role, so we're going 0 to 2 pi. And V is going to go from 0 to 1. And now how do we know that this is a cone? It's because I'm really seeing in the UV plane, in the RZ plane, I'm really looking at RZ is V times the vector 2 comma 1, and I'm going up until 1. So this is the picture in the R theta plane, in the RZ plane, and so the total surface is like this cone right here. Okay, and in fact, let me scale it up. So the real picture that we're going to get is this big old cone. It's opening widely, and I can show you what the partial vector fields are before we even compute them. So the partial u, I guess I've done that in blue before. So here's partial u. It acts like theta, so it goes around this way. That's partial u. And now partial v, you can always find it by looking at the RZ plane. So because this is the tangent vector, which moves this way, then we know that this is how partial v is going to look. Comes radially outwardly from, this is kind of like the fibers of the cone. So that's partial v. Okay. So now in the problem, if I want to do any sort of flux integral, so this is something I want to say, I want to tell you what my positive direction is. So I'm going to decide, say, n is the normal vector field pointing inwards and upwards. So really, there's always only two choices of a unit normal vector field, either one or its opposite. So in this case, we're picking, it says my internet connection is unstable. Hopefully that doesn't persist. Okay, so that means the unit normal vector field is the one that kind of comes in like this. This one's coming right at your face, and this one's coming in like this. Okay, so that's n. Oops, it's really supposed to look orthogonal to the cone. And then the last thing we'll want is a vector field. So let's do v of x, y, z is, what did I say? X comma y comma 0. Okay, so let us like kind of sketch that. I'll draw that in green. So if you remember, if you kind of just cover up the z component and pretend this is a vector field in the xy plane, it just looks like that radially expanding vector field. So we have lots of these, we have this sort of vector field coming out right from the center, like a center lightning rod coming right out from the middle. We've got a lot of vectors going on. So probably shouldn't have drawn the purple and green, the purple and blue ones. But if you kind of look at the picture, at least let's look at what happens up at this point. You see that normal vector, that red vector is kind of coming in and up, whereas the vector field v is really coming outwards at that point. So we kind of expect that v dotted with n is going to be less than 0. Things are kind of flowing not into the cone, but sort of out of the cone. That's kind of how this vector field is moving. So we expect that the flux integral is going to be negative. So let's actually check. So let's compute. Okay, so to do this, we'll actually need a formula for partial u and partial v. Okay, so I get that from looking up here, and I take derivatives. So if I take some u derivatives, I'll get negative 2v sine of u, 2v cosine of u, and 0. And then we'll want a v derivative. So we'll have, I guess, 2 cosine of u, 2 sine of u, and 1. Okay, so let's compute really quickly partial u cross partial v. So partial u cross partial v, and then we'll see if this is the correct vector field, if this gives us the right thing. Actually, we can actually answer that right now. Like, let's look at the picture. So partial u is the sky blue, partial v is that purple, and just pick any spot on the cone that you like. Anyone will do. And if you do a right-hand rule, if we do blue first, then purple, I see I'm actually going to be pointing down and away. If I were with you in person, I'd be using my hand to sort of illustrate. But if you use your hand, you start going along blue and then flip up purple, your hand is going to be coming out. Wait, yes, out of the cone. Okay, so this thing is going to give us the negative answer, which is fine. We'll actually compute it. So let's do this cross product. Okay, if I do this, I'll get 2v cosine u. Then here I'll get 2v sine of u. And for the last one, I know I'm going to probably get some sine squared plus cosine squared. And in fact, I do get negative 4v, like sine squared plus cosine squared, but that's just one. So I did that kind of quickly, but you can also, again, check that this thing is going to give you, this is negative n, because if you look at the z component of this vector, it's negative, v is positive, so the z component is negative, and that means that the thing that we've computed, I'll draw it in orange for a second, we've actually computed this vector field, which has a negative z component. So we're trying to go for the red, so if you ever think you've got the opposite number, just flip the sign. Okay, so now we've got all the pieces that we need, I believe, so I'm gonna minimize some of this stuff so I can stay on the same page. Okay, all right, and so now let's actually compute the integral. Let's compute the integral, finally, first integral of the day. We're doing, I'm looking at the formula up top. So my C and my D are 0 to 1. My A and B are 0 to 2 pi. And let's figure out what the vector field is. So I'm not going to write x comma y comma 0. Instead, I'm going to replace what I have, my x of uv. So x turns out to be 2v cosine u. My y is 2v sine of u. Then my z component of my vector field is just 0. All right, and then what am I doing next? I'm dotting it. So that was, okay, that was this piece. Now I'm going to do this piece right here. So that gives me, okay, I gotta correct everything by a negative. So negative 2v cosine u, negative 2v sine u. Oh, goodness, okay, give me a sec. Okay, and then positive 4v du dv. All right, if I do this dot product out, you'll see that I actually just get, if I dot and combine the cosine squared, sine squareds, I'll actually just get negative 4v squared. That comes from the dotting the two, okay, this was the partial u cross partial v up here. That comes from dotting this and this plus this and this, and then I have plus 0 from that z component, dv du, and then I can just do this. So Lily asked, why am I correcting with the negative? Because I should have, because this tells me, if I look at this, the real formula for n should be the thing with negatives, 2v cosine u, dot, 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 dot. The thing we crossed was the wrong unit normal. It's just because the problem dictated at the beginning which is the correct sign we use. And I always just do partial u cross partial v first, just because of alphabetical order, but that doesn't always mean your math will agree. So the thing we computed wasn't quite the right n. We just needed to negate it, is what was happening there. And okay, so now we're able to, this is a, okay, integral, so I can actually do it in one swoop. So I got negative 4 from the negative 4. I get 2 pi from the 0 to 2 pi. V squared becomes v cubed over 3. And I'm evaluating between 1 and 0. So that's like this times 1 minus 0. And that's just this. And lo and behold, this number is a negative number. This is negative, and it is what we expected. Now, if we had used the other n, then we would have gotten a positive flux. And that would have also made sense with our picture, because if we did use this n, then we see that the green and the orange would be making acute angles around the entire surface. I mean, even here, it would always be making acute, and so we'd be racking up positive values in our dot product. So we're glad we got our negative right now. Okay. Okay. All right, let's do another example. So in this next example, okay, the surface is a rectangle in 3D space with vertices at, it's okay, I said 0, -1, 0, 0, -1, 1, 0, 2, 0, and 0, 2, 1 with normal vector field pointing, well, I'll just say 1, 0, 0. Okay, so let me draw this thing. So we're going to have 3D space. Let me draw the 3 points. So here's the first one. That was this. The next one is just 1 unit up. That was this one. This next one is I start at this point and run a couple units out here and then up here. So it has no x component. It's parallel to the YZ plane. There's my x. And my n is coming out this way. That is n. Okay, this is my surface S. And I'm going to tell you a vector field. The vector field that we'll be working with is v of x, y, z is, I said -y, x, 0. Okay, so this again is like in the previous case when our vector field didn't have a z component. So we can just cover it up, remember what that vector field looks like. It's in the 2D plane, and that's that rotating vector field. So to know what it looks like on the full picture, you just draw a whole bunch of those stacked up on top of each other, and those kind of look like a tornado. Okay, so it's like a tornado that cycles about this vertical z-axis right here. So it's going to do different things on different sides. So down here, we're on this side of the surface, it comes out of the surface like this, and then it kind of starts swooping around this way, but by the time we get to this part, we're going into the surface. So it's this sort of cyclone, and on different halves, on different pieces of the surface, it's coming in and it's coming out. So I would guess that we have that overwhelmingly what happens over here on this heavier side, this side with positive y, we see that like the picture really is v and an n. And so that certainly has negative dot product of v with n over there. And over here we had positive dot product v dot n because, okay, I don't like making it that thin. Here it's more so like that dotted with this thing. Okay, but because there's more area on the negative side, I would also guess, so we suspect that the total accumulation of this dot product, dA v over s, would be negative. That the total flux, that on the total, that the vector field is going into the negative side of the surface. Okay, so let's compute. So I'm probably going to have to shrink all this again. Okay, let's actually compute. So I need to parameterize this thing. And if you notice, I mean, you can always, this is a parallelogram. The surface is a parallelogram. And you can always parameterize a parallelogram like it's like a point plus 2 displacement vectors. So it's r of uv should be, I'm going to start at that base point, which is 0, -1, 0, plus u times my, I guess, my vertical displacement vector, which is going to be 0, 0, 1, plus v times the vector. Well, that's, okay, I'll do this. That purple one was this purple one, and this displacement vector is going to go into the y direction by 3 steps. So this is plus 0, 3, 0, and this actually tells us we have 0, comma, -1 plus 3v, comma, 0 plus u. So there we go. And both our u and our v are both between 0 and 1. Okay. All right, so what we always need to do partial u cross partial u and partial v. Partial u is equal to, this isn't so bad, it's literally just 0, 0, 1, and partial v is 0, 0, 3, 0. Okay, and so we'll want to take that cross product, and I can already tell you partial u cross partial v is, okay, it's like, okay, this is basically, this is k cross 3j, so this should be -3i. Yes, okay, so this is, let me think, let me just make sure. U, v, yes, okay. So that's 0, that's -3, comma 0, comma 0. And so we'll want to use, we'll actually want to use partial v cross partial u in this case again, which is 3, 0, 0. Okay, and so the total flux is the following. We have almost everything. Okay, so we're going to do the interval 0 to 1, 0 to 1. Our vector field v, but instead of writing this thing right here, I'm going to include my parameterization value. So instead of y, I'll be doing this thing. So -y is actually 1 minus 3v. Okay, x is 0 and then 0. So this was v of uv. I'm going to be dotting it with this thing right here, which is 3, 0, 0, and then du dv. Okay, so if I take that dot product, that's not so bad. We're doing 0 to 1, 0 to 1. This is 3 minus 9v du dv. Okay, the u doesn't do anything. I mean, if I've just integrated, so seriously, what that innermost integral kind of drops off and doesn't, it's like multiplying by 1, and we're doing 0 to 1, 3 minus 9v dv. And this gives us 3v minus 9 halves v squared, evaluated at 1 and 0, and that is just 3 minus 9 over 2. I think that's -1.5. So good, we got a negative number at the end of the day, which is what we thought based on at least what I suggested up here with there's more negative accumulation than there was positive accumulation of that flux integral. Like most of the time, the green was flowing opposite the red. That happens more often than the opposite. Okay, yeah, so being able to parameterize these surfaces is like a pretty powerful thing, and it's necessary to do in all of these flux integrals or scalar surface integrals. Okay, so I did make a online like handbook of them, so you can kind of see how to do a good chunk of them, and if you read through that, you might get a better intuition when you set these things up. Okay, let's do this next problem. Well, there's actually one thing I did want to say. So let's stay on this page for a second, and okay, you might think to yourself, we didn't really need to take this cross product. We already knew what the normal vector field was. The unit normal vector field was, where do we say it? I'll highlight it right here. It was 1, 0, 0. So I'll go into this next page. Why didn't we just do, we could have easily just done like 0 to 1, 0 to 1. We had, what was it? Oh crap, it was 3 minus, no. It was 1 minus 3v. And here we wrote our partial v cross our partial u. But you might just say, wait, we don't need that. I already know what n is. N is 1, 0, 0 du dv. Like, why did we go all the hassle with crossing the thing? If you just did it like this, you'd get a 3 times, you'd be off by a factor of 3. And the real reason is that if you can do it this way, but you would need to include your area element. This would need to be dA. So somehow, like a magnitude and a unit direction have to come into play. And so typically that's really nice when you just have the partial u cross partial v actually includes both the magnitude of dA and the direction of n. So that's why oftentimes we write NdA is seriously just partial u cross partial v du dv. This sort of has all the information that you need. So if you ever do like a flat object like this over here, where you already kind of know the vector field is just, you know, the constant 1, 0, 0, you can just use that and never have to deal with a cross product, but you will have to somehow figure out what the area element would be. So like, I just remember when I did it, when I was taking this class, I made that mistake quite often. And I realized I don't need to take a cross product. That's so silly. You know, just be cautious. Be cautious to make sure you're actually capturing that area element, which in this case was 3. Okay. And then Daniel asked, will that area magnitude just be area of the flat surface? It depends on your parameterization. It's that piece is there to sort of negate whatever choices you made in parameterizing, because all of us could have come up with a different parameterization of that surface that uses different parameters. I mean, I did 0 to 1, 0 to 1, but somebody could have had 0 to 1, 0 to 3. And in that case, your surface area element would probably look different. Yeah, okay. Okay, let's go 5. Okay, let's do page 6. We don't have that much time. We only have 8 minutes left, and I have 3 examples I'd like to do, but I mean, they're all kind of the same. So I'll pick the one that's actually showed up on a final. So let's do an example. This is final fall 2015. And it says, okay, it says S is part of the parabolic bowl, which is z equals 1 minus x squared minus y squared. But it's the part that features z is greater than or equal to -3 and y is greater than or equal to 0. So if I just draw this really quickly, it's like, here's my parabolic bowl, okay, and it kind of just does this thing. That's z equals 1. Down here is z equals -3. But then I'm kind of slicing off the positive y stuff. So it's this. Okay. It's a horrible drawing of mine, but it will do. And if I want to draw in the RZ plane, it really just looks like this. It's z equals 1 minus r squared, and it cuts off right here at r equals 2, because at 2 we get -3 down here. So to parameterize, you can notice that a parameterization over here is r of v could just be v, and z of v could be 1 minus v squared. That would parameterize, this arc, and it would move in the downward fashion. And so a full parameterization of the surface uses a cylindrical motivation. So you can see, we've talked about this many times before. this is also in the packet I wrote up. So this is v cosine u, v sine u. I'm getting this v from this v right here. And then the z is seriously just this 1 minus v squared. And the v bounds are controlled over here. We're going 0 to 2, and my u is going from 0 to 2 pi. Okay. All right, and then I need to tell what the vector field. I haven't even said what the vector field is, and also the downwards orientation. So the normal vector field is kind of coming in and down like this. That's the one. That's the direction that they've picked. Kind of more inwards, I guess. So, oh yeah, Daniel says shouldn't. Yeah, okay, good catch. Thank you, Daniel. Daniel caught me. It's the u should be going from 0 to pi. That's right. I actually have it written on my paper, but okay. Yeah, u definitely goes from 0 to pi because bird's eye view, it looks like a semicircle which cuts off right there. Excellent. That's right. Okay, good catch. All right, and then we've got downwards orientation, so where n is like in and down, and then I need to say what the vector field is. The vector field is, so they want us to compute v dot n sdA, where v is, what did they say? X, y, 2z. X, y, and 2z. Okay, so that's the problem. I actually did hack the problem. They didn't give the parameterization. I kind of jumped ahead. I jumped the gun on that one. So let me kind of minimize some of this stuff because we're getting there, but okay. So that's the problem. And let's compute. So to compute, we know we'll need to take partial u and partial v. We'll need to cross them. It's just kind of no way around it. So let's look at partial u. Well, I've got to take some u derivatives. So I got negative v sine of u, v cosine of u, 0. Partial v is cosine u, sine of u, negative 2v. Okay, and let's take the cross product. Let's actually try to get it right this time. So before we do any crossing, let's see. To draw the surface, it's okay if I draw the full thing. Partial v comes down, and partial theta comes, partial u is this way. So that was partial u, and that's partial v. And so if I do u first, I'm checking it with my hands. I can't do this in front of you, but oh, I only have 2 minutes left. Crap. Okay, so this is the correct order. So partial u cross partial v. This is correct order. Because I only have 2 minutes left, I'll actually just tell you what the cross product is, as I have it written on my paper here. So you might want to check this on your own, but I did this last night. This should be negative 2v squared cosine u, negative 2v squared sine of u, negative v. Okay, and then after setting up the integral and taking the dot product, the integral becomes, all right, it's 0 to pi. So I did do 0 to pi on my own last night, so that's good. And then 0 to 2, and it becomes, after a dot product, negative 2v cubed minus 2v times 1 minus v squared dv du. Okay, and then I trust that all of you could probably do this integral on your own. Yeah, I don't know what the final answer was. I didn't get the final answer, but I think that's all about the time that we have today. So I'll stop recording and I'll see if anybody has any questions. So let's do